Hello, Dipanvita.
Yes, sir.
So let's start with questions first.
Yes, sir. Definitely.
Okay. So the first question is on the electrical double layer.
Okay, sir.
The question is in
So,
a
have you taught sir any theory before this?
what?
Have you thought? Have you taught any theory before this? Before
No, 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 I
joining?
just start. No, no,
Okay, okay.
yeah. So just I'm going through that. So we will be going to discuss the numericals on Hammond's double layer model,
Hmm.
where we model a EDL formation at solid liquid interface as a parallel plate capacitance. So here, if you have, let's say this solid and fluid is there, suppose this plate is negatively charged, then there should be some diffuse double layer formation due to the fluid. So it is a fluid in which this EDL formed, and we model this formation of EDL as a parallel plate capacitor, where this potential is, say, let's say phi A and this is phi B. This is phi A and this is phi B.
Okay,
Then
sir.
this should go like this, and E electric field strength can be calculated as minus delta phi by epsilon naught, sorry, delta phi by distance between this plates, and that is going to tell the thickness of the EDL in Helmholtz model. Okay. So the question
Okay.
is,
Sir, will the formula be equals to minus delta phi by delta? Will it be minus?
how can you write delta phi? So that is phi B minus phi A. But
Yes, sir.
so then
No,
it should,
no. No, no, I'm saying that will it be minus, sir?
yeah, why not?
Minus delta phi by delta will it be?
Yeah,
Okay, sir.
E,
Okay, sir.
E is always minus
Okay, okay, okay.
del phi by d phi by dx.
Okay, okay, okay.
So electric field is always from high potential to low potential, but this negative sign when we are taking so phi B minus phi A, so that negative sign will be there.
Okay,
Okay.
sir.
So in a solid fluid interface, a solid is positively charged, due to which there is a formation of electrical double layer at the interface. Consider a Helmholtz double layer model to model the to model this ADL. Assume that monovalent ions are adsorbed on the interface such that each ion occupies 16 nanometer square area. So the question is, estimate the surface charge density estimate the strength of electric field and volt per meter if the monolayers are immersed in a solution of dielectric constant 100. And third, calculate the potential difference if the thickness of EDL is 0.5 nanometer. Okay,
Okay, sir.
so one ion has ion has 1.6 into 10 to
1% 20 bar minus 19 coulomb.
so that is per ion charge present. This amount of charge is present. So to solve this and let me know the answer, then we'll try to solve together.
Okay, sir.
Okay.
Sir, I have got the first answer. Sir, sir, can you hear me?
Hello, am I audible?
Uh,
Yeah. Oh, okay. I am. I think I was mute. So the correct thing is here. So if it is negative, it is positive. So it should go from minus to. So this should be like this, and this should be corrected to this, so that negative sign will not be there if phi
okay, sir, okay,
delta
sir,
phi is
okay, sir.
defined like this.
Okay, sir, let me correct it.
Okay. So what is the first answer?
First answer is 0.01 coulomb per meter square.
Yeah, correct. Try other thing. Next.
Yes, sir. Yes, sir. I'm trying the second one.
Surface charge density is. Surface charge density is
0.01 coulomb per meter square.
correct. So it's simple, just sigma we need to find, and that is ions.
By 16 nanometer square.
So that is 1.6 into 10 to the minus 19 coulomb
By,
per ion, and area by 1 of ion is.
yes, sir. 16 nanometer square.
So it becomes 0.01 coulomb per meter square. So this will go to 10 to the minus 18. Okay.
Yes, sir. Sir, I'm trying the second one.
Okay.
So the second one is 1.12 into 10 to the power 7.
Okay, we need to calculate it. So let's calculate.
Sir, I've got the answer.
Yeah. So am I audible?
Yes, sir. Yes, sir.
So the ideal is like this. That is plus that is minus, and this should go like this. And these electric field lines are like this. That's the minus. So E is nothing but sigma by epsilon naught.
Epsilon naught, epsilon r.
So that is 0.01 divided by 8.85 into 10 to the minus 12. And this 0.10
Into 100.
into 100. So what you get? What you get after solving it?
1.12
1.127
into 10 to the power 7.
volt per meter. Correct?
Yes, sir. Sir, what will be the value of EDL? Will it be 0.5 nanometer?
Yeah.
In the third question,
Yeah, 0.5 nanometer thickness.
Okay.
Good afternoon, sir.
Good afternoon.
Can you scroll a little bit back that I can write the question to the question?
Yeah.
Sir, the answer is 0.56 into 10 to the power 7.
Okay. Let her try. Then we'll wait for 2 minutes and see.
first question is 10 is to minus 2 coulomb meter square.
Yeah, correct.
Then let me write see the second question, please.
Yeah. So let's solve the third part. So third part, we need to find the delta, that is the
Delta equals to delta phi by I mean the strength of the electric field.
delta phi into E. Correct?
Sir, delta phi by strength of the electric field.
Yeah. So delta we have, that is 5 into 10 to the minus 9 into E, that is 1.12 into 10 to the 7. And we need to find delta phi. Delta phi is, it's 0.5 actually.
Electric field only mentioned in 10 to minus 7 volt per meter.
No, it should be 10 to the 7 volt per meter. 1.12 7 volt per meter.
I calculated it is 0.11 to 10 to minus 8. So that will be eventually 1.12 into 10 to minus 7 volt per meter.
No, it shouldn't be minus 7. It should be 10 to the 7.
Yeah. Yes, minus 12 I have it. Okay, yes. Yes. Suppose the more than one surface is there, then that many number will be multiplied.
No, that depends how the capacitance, like if you are modeling it in terms of capacitance, then you have two EDL as in a parallel plate capacitor, then it's like a two capacitors in a parallel. Then you have to resolve it like that and find the equivalent capacitance and all the equivalent things as usual, like the basic electrostatics thing. So that depends upon the how many electrical double layers are there and how you are modeling it. If you are modeling it as a capacitance in a Helmholtz double layer model, in that case, you have to arrange as a parallel plate capacitor, and you have to resolve it like that. So the equivalent capacitance you have to find out accordingly.
Sir,
Okay.
can I say something?
Yeah, say.
The delta phi value, it is coming 0.56 into 10 to the power minus 2.
Oh yeah, let me calculate. So it's become 5.6 into minus 1, and so it's 0. What it is coming? It should become delta 6 plus 3, and so 0.
Yes, sir, 0.56 into 10 to the power minus 2.
0.05.
0.0056, yes.
So that is volt. Correct?
Yes, sir.
Any doubt? Okay, let's try another question. So consider the,
Sir, can you show me the question number 3 again?
yeah,
Question, sir, not the answer.
okay.
So the third answer will be 5.6 into 10 raised to minus 2.
It should be -3. Yeah, it should be minus. Okay, so let's look at another question. The question is, consider the Helmholtz capacitance model for the formation of EDL at the metal electrolyte interface such that it leads to an electric field of 10 to the power 8 volt per meter. So first part is find out the surface charge density. Second part is if the permittivity of the solution is second part is calculate the capacitance of EDL if the potential difference generated across the ED across the plate of area 10 nanometer square is 0.01 volt. Third part is find out the distance at which potential difference drops to becomes 0.005 volt. Okay, so try this question and we'll discuss it. I can see the capacitance in it. Okay, try this and let me know.
So the first one is 0.04.
Yeah, what is the first one?
0.04.
So let's try this out. The surface charge density is E into epsilon naught. So E is 10⁸ into
0.044.
what?
0.044.
I think it's wrong. Dipanvita, what's the answer?
0.04.
What did you say? Zoom?
0.044. 1 more 4 at the end. I have, yeah.
And Dipanvita?
0.04.
0.04 only. Yeah?
Yes, sir.
Okay, let's check. So this multiplied by this give me 442.5 into 10
Yes,
raised to
sir, actually, my answer is also 0.0442, but I just rounded it off to something.
Yeah, actually, that is the answer. Actually, I told it 0.044.
Okay. So that's it.
Since it is 2 after decimal, so it will be 0.
What?
Sir, since it is 2 after the fourth decimal place is 2, so I'm rounding it off to 0.
Okay, no issues. So sigma is comes out to be this. And what's the unit?
Sir, the unit is meter per volt.
It's just coulomb per meter square.
Oh, coulomb per meter square.
Yeah, what is the second? Have you tried second?
No, sir.
No.
Not right.
Sir, 8.85 10 to the power minus 31 coulomb. Sir,
So let's try.
sir,
So
will it be
epsilon naught epsilon A by delta. Okay. So 8.85 is 12 into 50 into 10 into 10 cube minus 18 divided by delta. We don't know delta yet. So delta is nothing but 0.01 by E, and that is 0.01 divided by 10 to the power 8. So it becomes 0.01 into the cube minus 8. And so this becomes divided by, so this becomes 442.5 into, so this becomes 10 to the power minus 90 meter. However, this is not a realistic number, but can we check if we did any mistake? Did we? So delta should be area delta is in nanometer. Yeah, so we are calculating capacitance. Okay. Fine. So the unit of capacitance is
Coulomb.
okay. Is the answer correct? Is it matching with you? Dipanvita?
Sir, actually, I couldn't solve the problem.
Who told the answer?
Sir, I never told the answer.
Who's the other one? She told me the answer.
No, I haven't told actually. I didn't able to work out this question.
Oh, okay. So I don't know. I think I listened someone and then. Are you asking something else, Dipanvita?
No, sir. Actually, I didn't know the formula, sir. I was confused with the formula.
Okay, okay.
Sir, what is the unit of capacitance?
It should be more, no?
It should be Farad actually.
Faraday or more.
Farad.
Actually, I'm a pure chemistry student. I don't know anything about.
So SI unit of capacitance is Farad.
Faraday. Okay.
That means that 1 coulomb per 1 volt. This is Farad. So try third one and then we'll see.
Is it the answer is 0.05 nanometer?
So to check it. So how did you calculate it?
The
Can you help?
potential difference divided by electric field.
Potential difference divided by
Electric field 0.05 volt divided by 10 raised to 8.
so what you are calculating?
Delta, no?
Yeah. So what is that? So we need to
Delta is
calculate the
equal to potential
charge.
difference divided by electric field. That's what I calculated.
So
Delta
electric
psi by
already know
E.
that is 10 to the power 8.
Yes.
Delta 1 comes out to be 0.005 and give a minus 8.
Yes.
Correct?
So it will be nanometer. So 0.05 into 10 raised to minus 9 meter, which is equal to nanometer.
Yeah, correct. So any doubt in this all of these questions?
So there is a question is given in the assignment. There is 2 flat surfaces given. So
Yeah.
we are calculating only for 1 flat surface.
Like how did you calculate the electric field? It should be the so you are not calculating potential. You are how you are calculating electric field is is the electric field is due to the two charges, na? So like two plates, plus and minus. So that is like that. So the potential difference is because of the, so potential difference is there because of the two plates. There should be some potential difference. So as I told, so this potential difference is because of the two plates. No? If this plate is not there, then what should be the
But
potential difference? It will go to infinite.
so this is potential difference because there is a surface and there is a different type of monovalent ions are present, no?
Yeah,
So due to that, there is a surface having one charge and the opposite charge is present just
yeah. So
above
the
the
so
surface.
whatever the charges are there, because of that,
Huh.
the same amount of opposite charges are there.
Yes.
So the charge density should be same, no?
For number of surface also.
Number of surface.
No, I have a question doubt. Suppose we are calculating the all the problems which sir has calculated in the video and you are calculating. It is for one surface and where the one monovalent ions are absorbed on the surface, right?
Yeah, it is. Yeah, it is due to that surface only.
Okay, but if it is two surfaces are there, then how to do that?
So two surfaces means what? Like how can you align two surfaces?
I don't know, sir. So given in the question, I am in the doubt for that.
Maybe you are
It is written
confusing.
consider
You are,
two flat
you are getting
surfaces in two
confused with the. Maybe you are getting confused
here.
with the language. Just that only. Like here are the two surfaces. One is, so if it is plus sigma, let's say, then it is minus sigma. That's it.
Yes.
So if it is plus q, then it is minus q by A. Right?
Okay. So then also it is considered as it is given. It is two surfaces are there.
Yeah, the potential difference is because of the, so there is some drop that is because of the two surface, and then it is that only. So the electric field lines are from plus to minus and something is there, no? Some counter ion should be there. Then only
Yes.
there is some electric field. Otherwise, it's like a point charge having some infinite uh going in an infinite direction. The electric field lines are going in a some infinite direction. You don't know about that. So whenever we have, like if I am saying this plus q and minus q, and I have to write the electric field, so it should be k q1 q2 by r square, and this is the distance between them. So it is always this electric field is defined is always because of these two charges. Correct. Hello.
Yes, sir.
Did you
Yes,
get
sir. Yeah.
okay? If you have, if you go back and try, if you have still doubt, we will resolve it in the next class.
So this is a question of this assignment only. So I am having doubt on the S1 only. Otherwise, I am able to calculate
Yeah,
everything.
just try to read the question again because, like, whenever we are justifying the electric double layer in case of capacitance model, it's always the two parallel plates. It shouldn't be like
Okay.
some infinite. It's the two parallel plates that we are considering as a double layer, and the distance between two parallel plates is the thickness of that double layer. That's the Helmholtz model.
Okay.
Okay,
Okay.
just read and if you have any doubt, we'll resolve it. If you still have any doubt, we'll resolve it. Okay.
Okay.
Any other? Any other has having doubt? Any doubt?
Not
Sir, there's a question in the assignment. Can I read it out?
Yeah, tell me. Though I am not allowed to solve that question before the, but I can give you some hint. Tell me.
Okay, sir. Wait, just wait.
So can you tell me the question number, which question number you are talking of?
Yes, yes, sir. Sir, I'm talking about question number 4.
Okay.
The large particle and the polymer mixtures, that one. I have ticked the correct option, large particle and polymer mixtures. I don't know whether it will be correct or not.
So actually, sir has told this in the last week lecture. Just for a hint, I'm telling you that sir has clearly discussed that in the last week lecture that when there is this depletion interaction can occur. If you just go through it, then you will see. Okay.
So actually my conception was not clear, that's why I was asking.
No, I cannot clearly discuss this question right now, and I am because you have pointed out like this. If you, but this is discussed that when the depletion interaction will be occur, that is very clearly discussed. If you have any
Okay.
doubt that why and how, if it's in which molecule, then I will say tell that. But
Yes sir, yes sir, yes sir, you can say that.
no, but sir has told, sir has taken the different cases where he has told that when the depletion interaction will occur. So depletion interaction uh, occurs like when there is uh, no charge, no polymer adsorbed on the interface, and the two particles are close to each other, and there is a formation of depletion potential. So that is one case. Then there are other cases also. So just go. Now I'm not going to tell that. You have to.
Okay sir, okay sir,
I'm not
okay.
allowed to do that, but it is discussed in the lecture.
Okay sir.
Yeah, I think in the last week's in the depletion in the second last or last lecture it's discussed. I think in the depletion population maybe.
Okay sir.
Yeah. Anything else?
No sir.
Okay. Uh, so the last question we discuss and then we'll wrap up the session if you may not have any doubt. So the last question is if the ratio of overlap volume for the case of sphere, sphere, plate, and plate type colloidal particle is 1:2:3, then find choose the correct choose the correct option for the magnitude of the depletion potential. Okay, so options are so phi is the depletion potential for sphere particle, sphere plate and plate to plate. So can you tell this or try this and let me know the answer? Consider one thing I have to add this. Consider the pressure. Consider the same osmotic pressure for all the types. Okay. Just let me know the answer. Try this. Hello. Hello.
Yes, sir.
Yes, sir.
Any answers? It's an easy question here. What is V? P into V, isn't it?
Yes, sir.
So then P, if I have to compare the magnitude, then it should be P V into V overlap. So Phi, if I have to compare Phi, if I have to take the ratio of S's, then it become V volume is always positive. And we know this is to be 1 is to 2 is to 3. So the magnitude is highest for the case of this.
C option.
Why? The magnitude of this should be highest. The correct option is this, isn't it?
Yes, sir. Yes, sir.
Is it correct? Any doubts?
No doubt, sir.
Okay. Haruni, any doubts?
No, sir.
Okay, so if you don't have any doubt, then we'll wrap up the session. Otherwise, if you have any doubts, you can ask. Really.
Sir, can I ask one more thing?
Yeah, sure.
Not about this assignment. The questions we are going to get in the examination will be like the assignment only, or like the derivation what sir is
Yeah,
working out.
derivation should not be there mostly. It's only like the questions like you have to choose the correct options, and it's the simple like you have to you have to fill the digits mostly.
Not the derivation that sir is doing in the video.
I don't think I don't know about that. That's the different TAs who are working on that. I don't know nothing about it.
Okay. Fine.
Okay. Anything else?
So can I leave?
Yeah, tell.
Sir, when you are going to upload this?
Yeah, just today, as soon as I get it.
Okay.
Yeah.
So by tomorrow, please, sir.
Yeah, sure.
Thank you.
Okay.
Yes,
Anything?
sir. No.
Yeah.
Sir, can I now?
Yeah, sure.